Section 6.4, Work. This section deals with the idea of how much work it takes to perform a task. In physics, work depends on what is called a force. Intuitively, you can think of a force as a push or a pull. A specific example of a force is the force of gravity, which has a downward pull. If an object moves along a straight path with position function s of t, then the force on the object in the same direction is given by the second law of motion. F equals, in this case, just the mass times acceleration, which is equal to the mass of the object times the acceleration. And just remember that acceleration is the same thing as the second derivative of the position function. With constant acceleration, then the force is constant, and the work done is the product of the force and the distance that the object moves. So in a very simple case, work is just force times distance if our force is constant, and then of course the distance would also be a constant, and then that makes work a constant. In the metric system, the mass is measured in kilograms, the displacement is measured in meters, and time is measured in seconds, and we measure the force in what are called newtons. Capital N for Newton, which is equal to kilograms mass times acceleration. So this relates exactly to force, mass times acceleration, so kilograms times meters per second squared. If the distance traveled is in meters, then the unit for work is a Newton meter, which is also called a joule, which we abbreviate with just the letter J. In our country, we don't use the metric system, so we measure force in pounds, and distance is measured in feet. So the work done is a foot-pound. So notice here, pounds has that whole idea of mass and acceleration built into it. So that gives you an explanation of what's happening with a constant force and also the measuring units that we'll be using. But the big question for this section is, what if the force is varying? Imagine you're pushing a box along the floor. So you start at some point and you want to go from one point to another. So you start, but then maybe you get interrupted. So after you've started, you've stopped, but then you need to pick this back up again and then continue pushing the box along the floor. So you don't have a constant force over the whole time interval or over the whole distance from point A to point B. So what would you do to find the total work if you have this force that is varying throughout? So to figure this out, let's consider the concept that we've seen over the last few chapters. Suppose an object moves along the x-axis in the positive direction. So if you want to think of a simple visual, here's a line that represents the x-axis, and if we're moving in a positive direction, it means that we're considering moving to the right. But we just want to think of from point x equal A to point x equal B. And suppose f of x is a force that acts on the object at each point between x equal A and x equal B. So if you think you've got an object like, let's say, a box, you're going to be moving it this way, and the way that you're going to be doing that is by, say, pushing on it with this force f of x. So to figure out something related to work that would be total over this whole distance, we're going to divide up this interval into n subintervals. So it's like we're just cutting up our whole interval from A to B into n subintervals. And if we choose n to be large enough, then the ith subinterval, which you could think would be at some point along this path, the ith subinterval, delta x, will be small enough. So if we consider a distance between 2 points as being delta x, that will be small enough so that the values of the function on just that subinterval, that will be essentially constant. So are almost constant. If they're not constant, what could you do? Cut it up into smaller subintervals so that delta x is so small that in that interval, the force is essentially constant. So then for this subinterval, we can say that the work on that subinterval, w sub I, is equal to the function f evaluated at x sub I. So you can think that x sub I, but we've also been using a star for the most optimal point in that interval. So then work at the ith interval is equal to f of x sub I star times delta x. Remember that delta x would be the distance that is traveled in that ith subinterval. So we again have force times distance. That's relating us back to work. So now that's just for one of the subintervals. So we need that for all of the subintervals. So we sum the terms like these from 1 to n, and then send n to infinity, which is just like an abbreviated way of saying the limit as n approaches infinity, or you're letting n go to infinity. Then when we put all of that together, we get the following definition. The work done in moving the object from point A to B is found with W is equal to the limit as n approaches infinity of the Riemann sum I equal 1 to n of f of x sub I star times delta x. But we know from what we learned in chapter 5, that is the same thing as the integral from a to b of the function f of x dx. And this is what we will use for a function that is either varying or constant. This would also work with a constant function as well, as you're just going to essentially multiply the constant times the difference of the two endpoints. That's the distance that is actually traveled. So let's see how that works in an example. When a particle is located a distance x meters from the origin, a force of cosine of pi x over 3 newtons acts on it. How much work is done in moving the particle from x equal 1 to x equal 2? Once we find that, interpret your answer by considering the work done from x equal 1 to x equal 1.5, and also from x equal 1.5 to x equal 2. So here you can think, again, we've got the origin is essentially x equals 0. We're pushing this object in a positive direction, we can assume. So x equal 1 is where we start, and we're going to end up at x equal 2. Our force is a varying force because this is a function. Notice that that function depends on x, and x is talking about a distance from the origin. So just using our formula from the definition, work is equal to the integral, where our integrand is our varying force function, cosine of pi x over 3 dx, and then we are starting at x equal 1 and ending at x equal 2. So to do this, we're going to need some substitution. So I'm going to say let u equal pi x over 3. I know that I need to use substitution because I have a function which is linear, pi x over 3, inside of a trigonometric function. So it's giving me a clue that I need to use some substitution. So then in this case, if u is equal to pi x over 3, du is equal to pi over 3 dx, which means I can replace u for pi x over 3, and then I can also replace what dx is by just multiplying both sides by the reciprocal. Dx can be replaced by 3 over pi du. So that means in my integral, I'm going to replace cosine of pi x over 3 with just cosine of u. I'm going to replace dx with du at the end, but then the constant 3 over pi at the beginning. And while I'm at it, I should replace my limits of integration. So when x is equal to 2, that tells me that u is equal to pi times x over 3, so that's 2 pi over 3. And then when x is equal to 1, that tells me that u is equal to pi times 1 over 3, so that means u is equal to pi over 3. So that means my limits of integration in my integrand after the substitution, the bottom limit becomes pi over 3, and the top limit becomes 2 pi over 3. So now I integrate using antiderivatives. The 3 over pi is a constant, so that's just going to be factored out. The antiderivative of cosine of u is sine of u, and then I need to evaluate at 2 pi over 3 first, and then pi over 3 second. So I'll have 3 over pi times what I get from evaluating, sine of 2 pi over 3, and then minus sine of pi over 3. Sine of 2 pi over 3 is the same thing as sine of 120 degrees. That's in quadrant 2. Sine is positive there. And the reference angle for 120 degrees is 60 degrees. And sine of 60 degrees is square root of 3 over 2. Which is the same exact result you get for sine of pi over 3. Because that's the sine of 60 degrees. So we get an answer of 0 from this. So now this is why in part of the directions it said interpret your result by considering the work done from x equal 1 to x equal 1.5. So I'm going to do this in the margin just right above the example because we have a lot of the work already for us here. If you think about for splitting it up from x equal 1 to x equal 1.5, I can use the same antiderivative. I can use the same substitution that I got for x equal 1. I just need another limit for x equal 1.5. So I'm going to write down when x is equal to 1.5. That's the same thing as 3 over 2. That means that u is equal to, this will be pi times 3 over 2, and then divided by 3. So that's going to end up being pi over 2. So if I integrate from x equal 1 to 1.5 of cosine of pi x over 3 dx, I don't need to do my antiderivative step. I know what's essentially going to happen. I'm going to get 3 over pi times sine of u evaluated at the bottom limit will be pi over 3 and the top limit will be pi over 2. So 3 over pi sine of pi over 2 minus sine of pi over 3. So that ends up being 3 over pi times 1 minus, and then we already saw that sine of pi over 3 is the square root of 3 over 2. So now, what do we get when we evaluate from 1.5 to 2? Well, 1.5 to 2 of cosine of pi x over 3 dx. That would be 3 over pi times, this will be sine of, as we already saw when x is equal to 2, the upper limit is 2 pi over 3. And then 1.5, we know that that's going to give us sine of pi over 2. So this ends up being 3 over pi times square root of 3 over 2 minus 1. So now, notice what we get. These two results are opposites of each other because the numbers 1 and square root of 3 over 2 are switched in the subtraction. When you add them, they add up to 0. So what might be happening here? Maybe just think of, we've got a function that is positive for one part of this interval and then negative for the other. So when we add up their total area, they add up to 0. That would be if we were just thinking in an abstract sense of the integral. So in the context of this problem, what do you think might be happening? Well, this function might be pushing in either direction along this distance, right? So you could have a force that is acting in a positive direction, but then a force that's acting in a negative direction. Cosine is a function that has positive and negative values. So this is essentially just oscillating back and forth. A little note on this problem that relates to just the substitution step. This helps with trigonometric functions. So if you have the antiderivative or the integral or indefinite integral of cosine of some constant times x dx, you can think that what we got from this example, we had that constant was pi over 3. That ended up with the reciprocal of that constant outside of the function, which then was outside the antiderivative of sine. So in this case for cosine, we saw that this was really 1 over a times sine of ax. If you were doing an indefinite integral, you'd of course have plus c. Same thing would work with sine of ax. You essentially would just have 1 over a, and then the antiderivative of a positive sine function is a negative cosine ax. You can use the substitution step like we did, but it might become more helpful to you if you just start to remember this with sine and cosine. That constant that's being multiplied by the variable, you just reciprocate it and it's out front of the antiderivative. Now let's look at two examples that come from the homework, which get a little bit more specific. So instead of considering an object being moved along an axis, this first example is going to be looking at what is called the work done to compress or stretch a spring. So this comes from the homework, and the question says, a spring has a natural length of 4 meters. It requires 48, and this should not be a J, it should be an N for newtons, for force. It requires a force of 48 newtons to stretch the spring to 7 meters. Calculate the work required to stretch the spring from 9 meters to 13 meters. Round your answer to the nearest hundredth if necessary. So this is going to need a concept that's called Hooke's law. And Hooke's law says this: the force required to maintain a spring stretched x units beyond its natural length is proportional to x. To understand what this means, imagine that you have a spring in your hand. So when it's just sitting in your hand, that means it's at rest. But now, if you were to stretch it, there is a force that you have to exert in order to keep it stretched and to keep it from springing back to its resting, or what's called equilibrium, state or position. If you're not familiar with a spring like a slinky or something like that, this works the exact same way with a rubber band. You know what a rubber band looks like. It's at rest if it's just sitting on a table. If you were to pick it up and then stretch it and then let go, it would go back to equilibrium. So your force that your hand exerts to actually keep it stretched, that's this concept of Hooke's law. So now Hooke's law says if f of x is that force that's required to hold the spring stretched out, that force is proportional to how many units you've stretched the spring out, which is x units. So quite simply as an equation, it means f of x, that force, is equal to k times x, where k is a positive constant called the spring constant. Hooke's law holds provided that x is not too large. Intuitively, if you think x is too large, you've stretched it out too far, you're essentially going to break the spring. So what we're given in this problem is that when x is equal to 3 meters, since 7 meters is 3 meters from its at-rest position of 4 meters long, then the force required is 48 newtons. So if you're just holding it 3 meters past its equilibrium state, that takes a force of 48 newtons. We can use that information to find the function that models the force for any value x. So let me write that down first. We're given that f of x is equal to k times x. We're also told that it requires 48 newtons if you want to hold that spring 3 meters stretched out from its equilibrium length. So now what this means is that K is equal to 48 divided by 3, or 16. So this now tells us the force for this spring. F of x is equal to 16x. And now you can use this for any distance stretched beyond 4 meters. So we can then use this to find the work done in stretching the spring from x equal 5 to x equal 9. Because again, if you want to stretch the spring from 9 meters to 13 meters, you have to think how this relates to its natural length of 4 meters long. So if it's 4 meters long, then it's another 5 meters to get to 9 meters. So you're going from that, x equal 5, to x equal 9, which is the longest length of 13 meters. So our work is just the integral from x equal 5 to x equal 9 of our function f of x, which is 16x, and then we are integrating with respect to x. So the antiderivative of 16x will be 8x squared, and then I'm going to be evaluating at 9 and then 5. So this gives me 8 times 9 squared, which is 81, minus 5 squared, which is 25. So 8 times 56, and 8 times 56, 448. And this would be joules. All right, one more application question, also coming from the homework, which gives a little bit more of a concrete understanding of work instead of just the abstract sense. Here we're going to look at calculate the work done to lift a cable. So in this question, a cable with length 5 meters has a mass of 30 kilograms and is hanging off of the side of a building. Acceleration due to gravity is g equal to 9.8 meters per second squared. Find the work done in winding up the cable. Round your answer to the nearest tenth if necessary. So the first thing that I want to do to set up this problem is just imagine our building. So there's our building, and it's 5 meters high, and we are winding up this cable. So maybe we'll think, here's the pulley for the cable, and the cable is hanging down the side of the building. What I want you to think of with this is, as you're winding the cable up, do you think it will get easier as the cable is getting closer to the top? It will, because you'll have less cable hanging over the side of the building, so the weight would be decreasing. Now here, we're not using weight in pounds, we're using mass. So when it's fully extended, the greatest amount of mass is hanging over the building. But as you're getting closer to the top, there isn't much left to pull, so the force does start to decrease. This is giving us a clue that we have a varying force that it's going to take to pull this cable up. So what might help us is, let's imagine the 5 meter cable hanging off the side of the building and divide it into n subintervals, just like I did from the beginning of this section. So I'm going to say that x equal 0 is the top of the building, because essentially that means I'll have no cable length left to pull up. And x equal 5 will be at the bottom. And I'm just going to choose some x point, let's say here, and that's again our x sub I star. And we're going to think, all right, what would it take for me to lift the cable from that point just up a distance of delta x? So we're going to divide it into n subintervals, and each length of the subintervals is delta x meters. We can also think that if the whole 5 meter cable has mass 30 kilograms, that means 30 kilograms for 5 meters. That's the same thing as saying 6 kilograms per meter. So 1 meter would have mass 6 kilograms. So the mass of the part of the cable in the ith subinterval would be 6 kilograms per meter times the delta x meters. So mass of the cable in the x sub I star section is 6 kilograms per meter times the length of that one section, which is delta x meters, but of course that's just 6 delta x kilograms. That's the mass of that part. Then the force acting on that part due to gravity would be the mass, 6 delta x kilograms, times the acceleration due to gravity, which is 9.8 meters per second squared. So that tells us that the force function f of x sub I star is equal to 58.8 times delta x. And this would be the force that's acting over the distance x sub I star, because essentially we're thinking of lifting it up to that point. So then the total work done over this section is W sub I equal to 58.8 times x sub I star delta x, where I've just rearranged the terms because we're used to, when I find the total work, I'm going to be looking at the limit as n approaches infinity of the sum from I equal 1 to n of 58.8 x sub I star delta x, which is really just the same thing as the integral, and now we're thinking of when x is equal to 0 to x equal 5, 58.8 times x, and then dx. So you don't obviously have to go through this whole setup when you see a problem like this. Now you can just think, all right, I need to figure out some expression for my force and then some expression for my distance. X is really just standing for the distance. The force that we have here is essentially the mass times the acceleration due to gravity. So 6 times 9.8, where I had to split up the mass for just a 1 meter section. And then I'm integrating with respect to my variable in this case, which is x. So then the antiderivative of 58.8x is going to be 58.8 x squared over 2, and then I'm evaluating at 0 as the lower limit and 5 as the upper limit. 58.8 divided by 2 is 29.4, and then times x squared, which is 5 squared, and then minus 0 squared. So this gives me 29.4 times 25. And that gives me 735. And since we're again measuring in the metric system, this would be joules.